Hello, Chem 1A. This is Chapter 8, Lecture Video 4. We're going to be talking about how to calculate the wavelengths of light that are being absorbed or emitted by our molecules or atoms when electrons move energy levels. So, as we began talking about in the last lecture video, when an electron moves from one energy level to another, this is going to either occur when it absorbs or releases energy as well at the same time. So, when atoms emit light, this is due to an electron dropping from a higher energy level to a lower one. So, for instance, if our electron was at energy level 2 and it dropped down to energy level 1, at that same point in time when it did that, because it's going to a lower energy state, it needs to release that energy, and it will release it as a wavelength of light or a photon of light. If we go from a lower energy level to a higher one, the opposite is going to occur, and we're not going to release light, we're going to absorb light. And that would be required in order for the electron to move to a higher energy level. Now, the equation that we use is known as the Rydberg equation. Now, this equation only works for hydrogen, but it actually allows us to calculate the amount of energy that would be needed for an electron to move from one energy level to a different energy level in an atom, specifically a hydrogen atom. This is a constant, right? So Rydberg constants are, Planck's constants h, speed of light, which is a constant in a vacuum, also a constant. If we multiply these three values together, you get 2.18 times 10 to the negative 18 joules of energy. So that's how I probably will give it, is actually using this number here, the 2.18 times 10 to the negative 18 joules on your equation bank, because we don't really ever use it any other way. Now, when an electron moves, like we just talked about, if we're saying it, hey, it's at this energy level 1 ground state, and it absorbs some energy, and it goes up to energy level 2. How much energy would it need to absorb? We can use this equation to calculate that. In this case, n initial would be 1, and n final would be 2, and we just plug in. All right, again, you don't need to memorize this equation. It'll be provided for you on your equation bank. Now, at the same time, if that electron then decided to drop back down to energy level 1, the energy is going to be equal, just the sign will be different, right? Because we're releasing energy as opposed to absorbing energy. Okay, so we'll do some problems on this in just a second. Oh, sorry. We'll talk about how this can be applied, and then we'll do a problem. So one of the things that we see pretty often is what we call a gas discharge tube. So this is what this guy is here. It's a gas discharge tube, and inside here we have a gas. And we run an electric current through it. So there's electricity running through this system. And when that happens, the gas actually, a lot of electrons get shoved up into higher energy levels, because electricity is a form of energy. And when they get shoved up to a bunch of higher energy levels, well, they didn't really want to be there. Life in general would prefer to be at a lower energetic state. So, or anything in general should be at a lower energetic state. We always go towards that. So as the electrons get bumped up, they start dropping back down. And when they drop back down, they give off light. And that light can be passed through a wavelength selector, like a prism. And that prism will break the light up into the different wavelengths that make it up. Right? And we can see what wavelengths these are. Now, each one of these different wavelengths here corresponds to a different electron transition, an electron moving from a different energy level to another energy level. Each one is different here between the four different lines. And this is the one for hydrogen. Now, we can actually, this actually was proof that Max Planck's idea that energy was quantized was legit. Because as you can see, only very specific lines are being shown here on this scheme here. And that's because only very specific lines actually exist.
as far as transitions. So just to kind of give you an idea, here's a bunch of different spectra for hydrogen, neon, and mercury. And as you can see, there are different numbers of lines present. These are all only the lines in the visible spectrum. There are more lines just that we're not seeing in the infrared and UV regions as well. But each one of these lines here corresponds to an electron dropping from a higher energy level to a lower energy level. And each transition is different between each different line because they're at different energies. So here's some examples of all of that. Now, I don't care if you know what the Lyman, Balmer, or Ritz-Passion series are, but there is a sapling learning question on this. One of the things that you kind of just need to know, just for sapling, not for my tests or quizzes, so if you're having trouble on that sapling problem, just look it up, is what the Lyman series means. And if you look at the Lyman series, all of them are going from a higher energy level to a lower one, but specifically all of the arrows are ending at energy level 1 for the Lyman series. But for the Balmer series, it's a little bit different. They're all transitioning to a lower wavelength or lower energy level, but they're all going to energy level 2. And finally, for the Ritz-Passion, notice all the energy, all of the transitions end at energy level 3. And this is really the only difference between these different series. These are only for hydrogen, and that equation we learned is only for hydrogen anyways. We can actually calculate all of these wavelength values from our equation that we learned a couple slides back. And I'll show you how to do that on the next slide. Cool. So moving on, again, we can't see any of these two because we only see in the visible light, so our eyes at least. So we only actually, with our eyes, can see these 4 lines. Our instrumentation, though, in the lab can see these and these. We have technology that can measure those for us.
Okay, so let's do some example problems with our Rydberg equation. So let's calculate the energy absorbed or emitted when an electron moves from energy level 2 to energy level 4. All right, now the first question we have to answer is, well, was it absorbed or emitted? It's one or the other. You can't have both. And since we know it's going from energy level 2 to energy level 4, going from a lower energy level to a higher one, we know our correct answer is going to be absorbed in this case. Now we know delta E is equal to negative 2.18 times 10 to the negative 18 joules times 1 over NF squared minus 1 over NI squared. Or in this case, we can erase the n's and plug in our numbers. Our final n value is 4. Our initial n value is 2. And so we can plug those in, square the values, right? So it's 1/16 minus 1/4 in reality. And we can get our calculated value. Now we should be expecting a positive value because, again, it's an absorption. And you get about 4.08 times 10 to the negative 19 joules. Now this is for a single electron moving from energy level 2 to energy level 4. So, and this is a bullet, not a negative sign, sorry. So again, very small amount of energy is required to move one electron, but generally we don't have just one electron moving, we have many electrons. So what if we had a total of a mole of electrons? How much energy would that be? Well, the way we do this is now we have to use Avogadro's number, just like we did when we were calculating the mole of energy of photons would be present in a specific wavelength in a previous lecture video. So I'm going to take my 4.08 times 10 to the negative 19 joules and go, okay, hey, well, this is really per 1 electron. And I know that if I go, hey, well, there are 6.022 times 10 to the 23 electrons in 1 mole of electrons. I'm going to just use the symbol for an electron, E minus. I can calculate, right? Moles of electrons cancel. We're in joules per mole. I'm also going to convert this to kilojoules because it's going to be a large value. So there are 1,000 joules in 1 kilojoule here, and our joules will cancel and we'll be left with kilojoules. So let's calculate that. We get that you should be about 246 kilojoules per mole of energy would be required to move a mole of electrons from energy level 2 to energy level 4. All right, so let's do one last question. What was the wavelength of light absorbed? Well, we can actually calculate that from our energy per electron. We also know that energy is equal to hc over wavelength, Planck's constant times speed of light over the wavelength. And so this is going to be equal to 6.626 times 10 to the negative 34 joules seconds times 3.00 times 10 to the 8 meters per second. Both are constants, both will be provided, all over wavelength. Well, we want to solve for wavelength, and we know our energy. So we can set this all equal to 4.08 times 10 to the negative 19 joules of energy. Rearrange and solve for our wavelength, which would be equal to 6.626 times 10 to the negative 34 joules times seconds times 3.00 times 10 to the 8 meters per second, all over 4.08 times 10 to the negative 19 joules. And if you look at this, joules cancel, seconds cancel, we're left with meters, which isn't our typical wavelength unit, but we can solve this, and I'm just going to say it's equaled up there. What we get is about 4.87 times 10 to the negative 7 meters. Now, if we convert this to meters, we get 487 nanometers, which is a reasonable answer. I got 486. There's a rounding difference there between my first time and my second time. So, all right, if you guys have any questions, as always, please feel free to contact me via email to set up a Zoom meeting, come to office hours, or yeah, just ask the question via email as well. Any way you want.